Okay. One of the problems with our rules of inference and problems with our propositional functions and all of that idea is that it is incredibly tedious to formally write out every kind of sentence we want to write and then use all those rules of inference to show, hey, this works. And in a lot of formal mathematics, it can take pages and pages and pages and pages to get through even simple concepts. For those of you that are interested in seeing the absurdity this can be drawn to, there is a book called Maths Made Difficult. I kid you not, it takes 55 pages to describe and define the number 1. And another 20 some odd to prove that 1 and 1 makes 2. What the? Paraphrasing Carl Sagan, who said, if you wish to make an apple pie, first you must invent the universe. If you wish to show something is true, first you must decide what it is. And describing all of these through the lens of formal logic becomes incredibly tedious. On our Canvas page, there is a file that I posted for you guys called The Art of Proof. Yeah, that's not it. Where did I put that? Oh, maybe I just threw it right on the Canvas page. Let's go look. Come on, Canvas. On our Canvas page, there it is, The Art of Formal Proof. And I must tell you that some of the results looking at the art of formal proof talk about the way in which we write up formal arguments. This figure right here, that's a set of statements in a proof. That's about as clear as mud, isn't it? Does that make any sense to you? Maybe a little. I mean, let me put it actually in the recording. If I'm sitting here, okay, there's an existential, there's an or, there's another existential, there's an if then, okay, maybe, right? Now I want you to imagine trying to actually make an argument to someone and convince them this way. I think I'd rather have a root canal. This is disgusting. So, a lot of what we do in proof is actually, instead of proceeding from valid argument to valid argument to valid argument to valid argument, one formal statement at a time, do this in more informal language. And in that case, an informal proof is a logically driven argument. And there's a bunch of terminology here. And in most math texts, that starts with the idea of a theorem. A theorem is something we can show to be true. We can prove it. Usually it's an important thing. To that end, there are lesser versions of this, a proposition. In this case, not just meaning a statement that is true or false, but in proving, then we can talk about a smaller result being a proposition or a claim. And a proof of a theorem or a proposition or a claim is the sequence of statements following the rules of inference that demonstrate the truth. So at its core, a theorem's like a headline. This is true. A proof is the newspaper article. Why do we know this is true? What's our argument? What's our rationale? First important thing, like when we talk about our propositional functions, I have to have a universe I'm speaking in. So if I'm talking about geometry, I need to know what the base assumptions are for geometry. If I'm talking about number theory, I need to know what base set of assumptions we're dealing with. Dan, this is very much like specifying what set my X is part of, right? I have to specify the things I'm working in. We call that the domain of discourse or our universe of discourse. In a proof, we call that the axioms or the postulates. And these are assumed without proof. These are the assumptions you start with. In geometry, Euclid started with a couple of basic postulates. Things like there is a point and it has no length, no breadth, no width. A line is connecting 2 points infinitely in either direction. So he started with these. These are the things I'm going to work with. Once he laid out the postulates, the axioms, everything else should follow from that. We're going to write a bunch of theorems. We're going to write the proofs using the axioms and our rules of inference. Now, sometimes we'll have to do some work along the way. In order to show this big thing, I do a bunch of these little things. Those sorts of helper theorems are called lemmas. And in some cases, we'll prove a big result, and then out of it will come immediately, oh, then this is true, this is true, this is true, as consequences of that big result. And those are called corollaries. And last but by no means least, a statement that we don't know whether it's true or false. We hope to find a proof, but we haven't found one yet. It's called a conjecture. Now, some conjectures, we simply aren't there yet. We don't know whether this is true or false. We haven't found anything that proves it wrong. We haven't found anything that proves it right yet either. We'll talk about a number of different things. But all in all, this is about making an argument mathematically. So, questions on the terminology? most of the time, it is the method by which we make our argument that is of importance to us. What is the right way to attack showing something? So, our first method of proof is called a direct proof. And the best part is this is the informal version of a rule of inference you already know. This is modus ponens. All right. In order not to be too esoteric or too crazy, I'm going to try and do proofs that I think should be directly simple to follow. So I'm going to prove things about numbers. Integers, positive, negative, zero, whole numbers, no decimals, nothing weird at the moment. We might stretch that a little later and start working in fractions or start working in the real numbers. But I'm going to do proofs that are based on numbers because I'm pretty sure most of you know numbers. And I won't have to build up a giant pile of axioms or definitions to work in numbers. So let me start with two definitions or two axioms. What does it mean for a number to be even? Yes, ma'am.
When you divide it by 2, you will get 2 equal.
So when I cut it in half, I should have two equal things.
Yes, the 2 numbers should be equal to each other.
Okay, I have a little bit of a problem. Not a huge problem. I have $5. I want to divide it equally. Well, I get $2.50 to one person and $2.50 to the other person. Is 5 even?
You get 2 integers.
Aha! 2.5 is not an integer. Okay, so I need to addend your description just a little. I need to be able to say this is twice some other integer. So an integer is even. Let me give my integer a name. What do you want to call our integer? Number. We'll call it n. N. An integer n is even if there exists k, an integer, so that n is 2k. I divided it equally into 2 other pieces, and those 2 other pieces were also integers. Right? I took our n, and I said our n is 2 times some other integer. So I can't do that with 5, because there are no integers. The number I need is 2.5. That's not an integer. But 16, yes, that's 2 times another integer. 0. 0 is even, because it's 2 times 0. Negative 14 is 2 times negative 7. There's another integer where I can multiply by 2 and get the number I want. Okay. If that's even, how do I define odd? Is that?
N divided by 2 is not in the integers, like a set of all integers.
N divided by 2 is not in the integers. 5 divided by 2 is not an integer, right? But 3.5 divided by 2, wait, 3.5, talk to me in. I should have a leftover, right? If I divide it into 2 equal piles, I should have something left over. 5, I get a pile of 2, and a leftover. 17, a pile of 8, and a leftover. So we'll actually write the definition very parallel to this one. A common maneuver in mathematics is to try and set up all of our axioms to look similar in the way we write them. Interesting point. If I use -15, then my piles need to be size -8. 2 times -8 is -16. I need to add 1 to get to -15. I didn't say anything about subtracting 1, only adding. Let's go down. Okay, so we know what numbers are even, we know what numbers are odd. This matches with our intuitive idea. 365, that's odd. You know what it's supposed to be. Now I can be formal about it. I want to prove the following sentence. So I am going to write a claim. If n is odd, then n squared is odd. That's literally just an if-then statement. So I want to use modus ponens. Modus ponens, when I have an if-then and I start with the if, I should get to the then, right? But now I have to justify all the steps that go in the middle. Why do I know if n is odd, then n squared is odd? Well, the first thing I should do is try a couple. What's 3 squared? 5 squared? 7 squared? 13 squared?
69.
We can do, they're all odd, right? -17 squared is positive 289. They're all odd. It looks like this should work. Should. Underline it. Should work. But if I claim something, I have to be able to prove it. So, how would I write a proof about this? Well, let me go back to our modus ponens idea, to our detachment idea. I should start with the if part. I should start with an odd number. So let me start by assuming I have an odd number. What's it mean to be odd? We just wrote that down, didn't we? So I'm going to say the definition of being odd means this is true right here. So far, so good? This is what it means to be odd. We look like this. But I don't care about n. The conclusion over there says about n squared, right? So I want to show, eventually, somehow, that n squared is an odd number. All right. Let's look at n squared.
I was just gonna say you could square both sides of it.
Okay. Now what? Let's multiply that out. What do you get when you square that out? You out the algebra. In? First, outer, inner, last, all that garbage, rearranged, etc. Is that odd? It's certainly unusual, but it doesn't meet our definition of being odd. Unfortunately, no, it doesn't. To be odd, you must be of the form 2 something plus 1. That's not 2 somethings plus 1. Can I make it 2 somethings plus 1? Let's just rearrange. Clearly, I've got the plus 1. It's sitting there waiting for me. So I just have to worry about the rest of this garbage. If I factored out a 2, what would be left inside that set of parentheses? Now, we know k is an integer, right? So k times k is still an integer. When you multiply 2 integers, you get another integer. 2 is an integer. When you multiply an integer by 2, you get another integer. When you multiply an integer by 2, you get another integer. So the junk inside that parentheses is integer plus integer. But when you add integers, don't you stay in the set of integers? So all of this junk inside this set of parentheses, I don't know anything about this number except the fact that it's an integer. Let's give it a separate name. I don't want to call it k squared, 2k squared plus 2k anymore. I want to give it its own name. I'll call it L. Then, here's our little therefore symbol. Therefore, n squared is 2L plus 1. And that matches my definition of being odd. I did it. I did it. I showed it. If I were really writing in Latin and informal, I would say, and thus it has been demonstrated, which in Latin is quod erat demonstratum. So it has been demonstrated, QED. Not just a radio station or a Pittsburgh station. Now, please understand, one of the things I get asked on a regular basis is, so in what? Big deal. I agree with you. This is not a huge, earth-shattering result. It isn't. But it is designed to be an introduction to the way we write these sorts of arguments. I'm not trying to prove something deep here. I'm trying to explain to you the reasoning we have to go through to create an argument. Now, you'll notice how I needed the axioms, the postulates, the definitions of working in the integers. That adding integers gives me an integer, that multiplying integers gives me an integer. I needed all of those things that you didn't realize you knew you already knew. That was information you had in your back pocket and just never thought about it in that fashion. Questions? Yes, ma'am.
Couldn't you have, like, I understand most of it, but calling the statement L I don't understand why you could do that, because in the line beforehand, you could put 4K squared plus 4K equals L, like you could call that a variable L.
I could. If I call this the variable L, then my number looks like L plus 1. Is
Okay.
that odd?
No.
I want it to match the form of my definition. And the form of my definition is 2 something plus 1. So I had to pull that 2 out and then say, oh, this is 2 something plus 1. There's my something. That looks like the form I want. This is the downside, is I have to try to figure out where am I trying to end up? I'm trying to end up with n squared is odd. What's it mean for n squared to be odd? N squared has to look like 2 thing plus 1. By the way, you don't have to call it L. You can call it anything. Call it Frank. I don't care. More questions. Direct proofs require us to have a handle on the universe of discourse, the things we are taught. And one of the problems in math, in programming, in any sort of formal, rigorous situation is connotation. This word means a certain thing, but it also has other, the meaning better be well defined here. And so when we talk about geometry, we talk about points and lines and planes, and those ideas are rigidly given to us at the beginning of Euclid. Now, Euclid basically cribbed this from every other geometry book he could get his hands on in Alexandria, and then he wrote his book called The Elements, and it starts with, here are my 5 starting postulates. Ready? Here we go. But if you don't start with the agreement on what those things mean, then you're in a lot of trouble. If I say the word polynomial, I know algebra class was a long time ago, but what does polynomial mean? You can give me examples if you want. What are things that are polynomials? I'm really stretching your heads because it's been a long time since you did some of this. Dan?
Yours each having a variable, or the third one being just a regular.
So you're specifically thinking of quadratics, right? Like some number x squared and then some number x and the number on its own, right? But I can have any power I want, right? X to the 17th plus 2x to the 4th, right? And some of those numbers can be 0 and some of those numbers aren't. The one thing you will not see in a polynomial under the accepted definitions in algebra are powers that are fractions. So you won't see x to the 1/2. That's a square root. It's not a polynomial. You won't see x to the 0.7. Doesn't work in a polynomial. You won't see x to the -1. That's a 1 over x. That's division. That's not a polynomial. I wrote a paper about changing the whole number to a fractional number. And I said, this is not a polynomial anymore. What does this mean? Well, that was part of my PhD thesis. I got into a year-long argument on the internet. Again, sounds perfectly normal to most people, over the definition of a polynomial. And I went after 200 different sources. And I said, find me one source that agrees with your definition of polynomial. He said, they're all wrong. I said, you're a crackpot. Goodbye. If we don't start with some common language, none of this is going to work. I'm going to stick most of the time to numbers, but eventually we'll start branching out and looking at other things. More questions? So the first method of direct proof. Start with what you started as your hypothesis. We said if n is odd, so start with n being odd. And then you work forward from there. You say, okay, what's the consequence of being odd? What's the consequence of that? And we keep developing what's the consequence until we end up at our conclusion. In the best of all possible worlds, this is a straight line path. It ain't very often a straight line path. But now I think to myself, hey, wait a minute. We had other logical sentences that were equivalent to our if then. There were three different sentences. There was the original conditional, and then there were three others.
Not P is equal to Q.
Not equal to, but
If not P, then not Q.
right, our contrapositive. Not, well, wait a minute, not P, not Q. Wait a minute, not P, not Q. What statement is that? Is that there were the names, inverse, converse, contra, which one is this? The one with the negatives in there, that was the inverse. And those were not equal. As a matter of fact, the other one that was not equal was the converse. But those two were equal to each other. The one that is equal is our contrapositive. Which sentence is that?
If not Q, then not P.
So, here's an interesting idea. A proof of this is equivalent to a proof of this. A proof by contraposition or an indirect proof works the other way round. Now, let me start with this claim, which is again about odd versus even. If 3n plus 2 is odd, then n is odd. Great claim. Start by checking it. Pick a couple of numbers. A number of the form 3n plus 2. So 9's not going to work. But 8 would, right? Because 8 is 3 times 2 with 2 left over. So 8 works. 3 times 2. Yeah, but 8's not odd, so that's not going to work, right? 11. 11. 3 times 3 with 2 left over. N is odd. 3 times 3 with 2 left over. Okay. Seems to work, at least a couple places. But if I want to try and do this with a direct proof, if I did this with a direct proof, where would I start? So let's write the parallel first sentence to the problem we just finished. What would be the first sentence of this new problem? Ian? That would not be the direct proof version. So what if I'm trying to do this directly? I would say start with this, right? Suppose this thing is odd. That would be the direct version. So I'm going to try and do this with direct. Proof, direct. Suppose 3n plus 2 is odd. So far, so good? That's the same way we started the previous one. Suppose n is odd. Suppose 3n plus 2 is odd. Well, then, the definition of being odd, there exists some integer, k, with this number being odd. Now, my goal is to figure out that n is odd, right? That's what the n says over there. It says n with n is odd. Which means I need to get n all alone here. What happens when you get n all alone here? What was that, Rum? Oh, wait a minute. If I first I have to subtract the 2, right? So I have 3n is 2k plus 1 minus 2, that'd be minus 1, right? And then I divide by 3. Here's where I run into a big problem. Did you ever tell me what k is? Do you know that this is going to actually turn out to be a whole number? Oh, crap. I don't even know if that's an integer, much less whether it's odd or even. I'm stuck. I don't know how to get to the next step that tells me, oh, well, that thing must really be an odd number. It might not even be a whole number because you didn't tell me anything about k. I'm stuck. And this is a case where, unfortunately, a direct proof fails to work. I don't know how to proceed. I've hit a block in the road. Remember, I said sometimes it's a straight path. I just ran into a wall. I don't like that. So rather than try and proceed from our hypothesis to our conclusion, let's try, Ian, as you suggested, the contrapositive. Let's try this as an indirect proof. Okay. So claim if 3n plus 2 is odd, then n is odd. Proof indirect. Ian, what was our starting point? Okay, I start with suppose this is not true. Suppose not Q. Suppose n is not odd. In other words, n is an even integer. Everything from here on down is going to proceed with that same sort of rule of inference idea. I know this is even. What does that mean? What's the consequence of that? What's the consequence of that? In as small and deliberate a step as I can make. Where do I want to end up? Starting with not Q, where do I want to end up? I want to end up with not P. I want to end up with this is not odd. So my goal now is to get to here and show that that thing is even. But I need to start with n is even. So what's it mean for n to be even? What's the definition of being even? Okay. There exists k with n equal to, oh, I should write integer here, shouldn't I? So let me actually write k is in the integers, like we did when we were doing our propositions, right? So here, Dan, this is exactly the thing you pointed out to me, right? I had to write the set. There, I wrote k as an integer. That's our funky looking z for Zolin for the integers. All right, so if n equals 2k, what do I want to look at? I want to look at this thing. So What can I do with that? But I don't know that that thing is even yet, right? I need to show it's even. The only thing I know that's equal to 2k is n. Oh, well, if I know n is 2k, let's put that in there. So let's shove that 2k in here. 3 times 2k plus 2. Great, wonderful, marvelous, beautiful. So what? Big deal. How does this help me? Roman?
Simplify for n. Solve for n.
But if I solve for it, I'm going to get right back to here. I'll cancel the 2's. I'll divide by 3. I'll get n equals 2k, which puts me right, unfortunately, in a circle. Not an uncommon occurrence. Oh, I can use an algorithm. My goal is to end up with 2 times stuff, right? Because that's what it means to be even. 2 thingy. Wait a minute. 2 times 3 times k. Go back to the rules for multiplying. You're multiplying 2 by 3 times k. Couldn't you multiply the 2 times 3 first, and then multiply the k? What's 3 times 3? Remember, my goal is to get 2 times stuff.
2 times 3k plus 1.
What do you know about the stuff inside the parentheses there?
It's the equation, it's in the form of odd from what we got at the top. Or no, that would be 2.
It would only be odd if it were 2k plus 1. That's 3k plus 1. 3k plus 1 can be all over the map. It is an integer, though. I don't know what integer, but it's an integer, right? 3 times an integer plus 1, that's an integer. So let's give it its own name. What do you call it? Call it anything you want. I already used L. We'll call it M. Hey, wait a minute. What was on the left side of this? 3n plus 2. So I've just shown what? What is my conclusion out of this? This number is even. We've shown if n is even, then 3n plus 2 is even. The contrapositive of this sentence, Ian? What's the contrapositive of this? And isn't that what my claim was at the very beginning? That if 3n plus 2 is odd, then n must be odd. So notice I wasn't able to get there this way. I had to go backwards and negate it, my contrapositive. Wow. Some proofs can be done directly, some proofs can be done indirectly, some proofs can be done both ways. Some proofs can only be done one way. How do you know which one can be done which way? You don't. You don't automatically recognize, I should do a direct proof, I should do an indirect proof. There is no guaranteed method for identifying which one should be done which way. I wish there was. I'd download that into your heads right now. So what do? You pick one and you try it. Just like we did. We tried to do this result directly. Got someplace you got stuck and went, oh, what do I do now? And the result was, okay, let's try this the other way around. Two sneaky corollary ideas here. Go back to the truth table. If I give you an if-then sentence and the if part is false, what do you know?
Statement is true.
So if I start from a false premise, then there's nothing for me to prove. The if-then part is automatically true. My proof is a vacuum. I don't have to prove anything. It's automatically true when the hypothesis is a false statement, thus a vacuum. If the moon is made of green cheese, then I am standing on the ceiling. True sentence. Stupid, but it's true. The other side of this, if I know the conclusion is true, then the statement, if P then Q, is either T arrow T or F arrow T, right? I don't know what P is, but if Q is true, it's got to look like one of those, yes? What do you know about both of those statements? They're both true. A proof that rests on the truth value of Q is called a trivial proof. Now, I'll do some examples of some that are direct, some that are indirect, some that are vacuous, some that are trivial, but run up against the clock. So we will do those on Wednesday. I will see you all then. If you came in late and you still have homework for me, please bring it to me. I will see you on Wednesday.